The deepest parts of the ocean floor are littered with trillions of dollars worth of minerals. And until recently, no human being had any idea how to get them. Beneath more than 4 kilometers of crushing black water, scattered across vast stretches of the Pacific, Atlantic, and Indian Ocean floors, lie billions of potato-sized rocks called polymetallic nodules. Inside them, manganese, cobalt, copper, nickel, the exact metals that power electric vehicle batteries, wind turbines, and smartphones. The global seabed is estimated to hold more manganese than all land-based reserves combined, more cobalt than the entire Democratic Republic of Congo, the country that currently supplies over 70% of the world's supply. The potential value of these deposits runs into the tens of trillions of dollars, and the race to extract them, using machines that have no precedent in the history of engineering, is already underway. This is how deep-sea mining works. Step 1. Finding the target. Before a single machine enters the water, the operation begins with mapping. Survey vessels equipped with multi-beam sonar sweep across thousands of square kilometers of ocean floor, building three-dimensional maps of the terrain at depths between 4,000 and 6,000 meters. Remotely operated vehicles, ROVs, are then deployed on tethers, stretching nearly 4 miles down, equipped with cameras, sediment samplers, and spectrometers that analyze mineral density in real time. This phase alone can take years. A single mining contract zone in the Clarion-Clipperton Zone, the most mineral-rich region of the Pacific, typically covers an area larger than Germany. The nodules that survey teams are hunting took between 5 and 20 million years to form, growing at a rate of roughly 1 centimeter every million years, accreting layer by layer around a microscopic seed, like a pearl, but made of metal. They sit loose on the surface of the sediment, which means they don't need to be blasted or drilled. They just need to be collected. That sounds simple. It is not. Step 2. The collector. A machine built for another world. The centerpiece of deep-sea mining is the seafloor collector vehicle, and it is unlike anything operating on land. Picture a machine roughly the size of a city bus, or 2 buses joined together, mounted on wide rubber tracks designed to distribute its weight across soft sediment without sinking. It is lowered on a massive umbilical cable from a surface support vessel, descending for hours through complete darkness and pressure that reaches 600 times what you feel at sea level. At that depth, water compresses with enough force to crush an unprotected human body to nothing. The collector is engineered to withstand it. Once it reaches the floor, it begins moving at roughly 0.5 kilometers per hour, slower than a walking pace, using a combination of hydraulic water jets and suction to lift nodules off the sediment surface. The jets loosen material, a suction intake. The diameter of a dinner plate draws the nodules and surrounding water into the machine's collection system. Powerful internal screens and separation chambers then sort nodules from sediment, discarding the sediment back through exhaust ports while retaining the mineral-rich rocks. The discharge plume this creates, a billowing cloud of fine sediment particles, is one of the most debated environmental variables in the entire industry. Regulators and scientists are still working to understand how far it travels and what it disrupts. The nodules that survive the collection process are then pumped upward through a riser pipe, a flexible tube stretching the full 4 kilometers from the seafloor to the surface. This riser system works like an airlift. Compressed air injected at the base creates buoyancy that carries a slurry of nodules and seawater toward the surface at speeds of several meters per second. Engineering this pipe to handle that pressure differential, that distance, and that flow rate without rupturing or blocking is one of the central technical challenges of the entire operation. A single pipe section failure at depth could mean losing the entire system. Step 3. Surface processing. From slurry to separated ore. When the nodule slurry reaches the surface, it arrives aboard a purpose-built production support vessel, a ship the size of a small oil tanker, purpose-designed as a floating processing plant. On deck, dewatering screens and vibrating separators remove the seawater from the nodule mass, which is then conveyed into storage holds. The seawater, now carrying fine sediment particles, is treated and discharged back into the ocean, ideally at depth, away from the biologically active surface zone, though the exact depth and method of discharge is still being refined by environmental regulators. The International Seabed Authority, which governs international waters, has been developing a mining code since the 1990s. As of the mid-2020s, no commercial-scale operation has yet received full extraction approval, though several companies, including the Metals Company, Global Sea Mineral Resources, and Deep Green, have active exploration licenses and pilot operations running. The nodules themselves, once dried and stockpiled on board, are eventually offloaded at port and shipped to smelters. Unlike traditional mining, where you blast rock and spend enormous energy separating a tiny percentage of valuable material from worthless rock, polymetallic nodules are remarkably concentrated. A single nodule can contain 2 to 3% manganese, 1 to 1.5% nickel, and measurable quantities of cobalt and copper all in one piece. Compared to copper mines on land, which often process ore containing less than 0.5% copper, these nodules are extraordinarily rich, which is part of why the economics are so compelling, despite the staggering cost of the extraction infrastructure. Step 4. Refining. Unlocking the metal inside. On land, the nodules undergo hydrometallurgical processing, a chemical extraction method that uses sulfuric acid or ammonia solutions to dissolve and separate the individual metals from the nodule matrix. The nodules are first crushed and dried, then fed into large pressure tanks where the acid solution strips away the metal ions in a controlled chemical reaction. The resulting solution, called a pregnant leach solution, carries dissolved nickel, cobalt, copper, and manganese in liquid form. Solvent extraction and electrowinning then isolate each metal individually. Electrowinning works by running electrical current through the solution, which causes pure metal ions to deposit as solid metal sheets on cathode plates. The sheets are then stripped, stacked, and sold. 1 metric ton of processed nodules yields roughly 250 kilograms of manganese, 15 kilograms of nickel, 10 kilograms of copper, and 2 kilograms of cobalt. At current market prices, that cobalt alone, used in every lithium-ion battery on the planet, is worth more than $50. Across a full-scale commercial operation processing thousands of tons per day, the numbers become extraordinary. And critically, because deep-sea nodules don't require the same land clearing, tailings dams, or acid drainage management as conventional mines, their land-based environmental footprint is dramatically smaller. Life cycle analyses by independent researchers suggest deep-sea nodule mining could produce roughly 70 to 90% less solid waste than equivalent land-based nickel production. The trade-off, of course, is the ocean floor itself, a habitat we are only beginning to understand. What it means: the battery in your electric car requires between 8 and 10 kilograms of cobalt. Your laptop battery uses around 30 grams. Every phone in your pocket contains metals that currently come from mines in some of the most politically volatile and environmentally fragile regions on Earth. Deep-sea mining doesn't promise to solve every problem in the global metals supply chain, but it represents something genuinely new, a form of industrial extraction that operates entirely outside the terrestrial world, in a realm we've barely explored, using machines that would have seemed like science fiction 20 years ago. We built towers into the sky, then drilled into the earth, then tapped the shallowest edges of the sea. Now we are sending machines, the size of buildings, into the deepest, darkest corners of the planet to harvest rocks that have been sitting there since before our species existed. The metals in those nodules built the modern world once already, in the cars and cables and circuits that came before. The question is what kind of world we build next, and whether we can do it without repeating the mistakes we made the first time. What do you think? Is the deep ocean a resource to be mined, or a wilderness to be protected? And can it be both? If this kind of industrial deep dive is what you're here for, subscribing is the best way to make sure you don't miss what comes next.